I've heard that a lot of you guys have been missing my intro, so I thought that I'd bring it back. Hey, what's up guys? My name is the Cherno. And welcome to another video. So today we're going to be doing another one of these kind of 1 hour challenge things. Last time I did this, I made a game in an hour. Check out that video if you haven't already. Basically what I did is this guy called Danny made a game in an hour using Unity, and I thought I would try and recreate that same exact game but using my engine inside Hazel, which is a very difficult task because Hazel is like barely an engine, it's barely capable of doing, well, anything. But nevertheless, I ended up making like exactly the same game, and it took me around 2 hours or so. And one of the hardest things to do in that challenge was all of the particles, because Hazel doesn't have a particle system. In fact, it doesn't even have like the rendering technology you would typically use to render particles. And so because of that, I had to write a particle system from scratch within that time limit. And I know that a lot of you were interested in how exactly I managed to pull that off. And honestly speaking, I don't think particle systems are that difficult, especially like the one that was needed for this game where it was just a bunch of colored squares. It wasn't like some kind of photorealistic textured, blending like smoke or something like that. It was a lot easier than that. It was just a bunch of colored squares with like a lifetime and all of that stuff. Not that difficult to do. So what I thought I would do in today's video is basically set up another timer and see if I could write a particle system from scratch within an hour. And I'm actually not going to use Hazel at all for this video. I'm just going to use my OpenGL base library. If you guys don't know what I'm talking about, check out that video there. Basically, I just made like an OpenGL kind of core base library that would easily let me just write OpenGL code on top of an already existing project. So that's the plan for today. We're going to see if we can write a particle system from scratch within an hour. But first, I want to thank Surfshark for sponsoring this video. Surfshark is a fantastic VPN service that makes online privacy protection easy and attainable. It encrypts all internet traffic sent to and from all of your devices and keeps your IP address hidden so that no one can see what you're doing online. And speaking of devices, Surfshark has no limit to how many devices you can use it on simultaneously, which is great. These days we spend a lot of time online, almost as much as we do sleeping, and because of that, the internet knows a lot about us. But by using Surfshark, all of your data is sent through a secure VPN tunnel so that no one can see it without your permission. Surfshark is more than just a VPN though, it's more of like a fully fledged security toolset. And because of that, it has a lot of other great features. For example, Surfshark also blocks ads, which is great because I tend to travel quite a lot and not have that much mobile data. And by blocking ads, I save a bunch of mobile data and also my browsing experience is just faster. And speaking of ads, have you ever been spooked by how an ad just seems to know exactly what you've been talking about? That's because your data is out there, but not with Surfshark. Surfshark have been amazing enough to give you guys 83% off and 1 free month. All you have to do is sign up using the link in the description below and use the code Cherno. Go ahead and sign up now using my code and make sure that you put it on all of your devices so that you're completely protected. All right, let's write this particle system. So for this video, instead of just showing you guys like a time lapse of me working on this thing and then later adding some voiceover, which let's be honest can be faked. Anyway, I thought that I would instead just take you through the completed code and explain a little bit more about how it actually works. I don't want to spend too long going through all of this, so if there's something that I've missed that you guys want to know, just leave a comment below and I'll try and just reply to that comment or make another video or something like that. And without further ado, let's get into this. So we have this class called particle system, and that's kind of it. There's just this C++ file, this header file, that basically makes up the entire particle system. The only additional file that is necessary for this particle system, or additional class, I should say, is this random class. And this is exactly the same random class as the one that appeared in that 1 hour game that I made in Hazel. And it's super simple. Again, something that you would definitely expect to be part of the engine. It's just using this kind of C++ standard library random like distribution function and random number generation algorithm here. And we're just setting up a static instance of that. And then there's just like this helper function here called static float. And, and that basically just returns a number between 0 and 1. So it just samples this random distribution here and then divides it by the highest possible number that will result from this function here. So basically, it gives us a number between 0 and 1. And that's great because it just makes it super easy. I love doing stuff like this because it makes it super easy to generate any random number I want. For example, if I want something that's between like, I don't know, 0 and 10, I can just call, this random float function and then multiply it by 10. And then obviously I'll get something between 0 and 10. If I want something between 1 and 0, obviously I don't need to multiply with anything. If I want something between 1 and 1,000, you guys get the point. It's really easy to just kind of whack that on. And to be honest, I kind of prefer that to functions with parameters where it's like, okay, specify your range or something like that. All right, that's the random class. Not going to spend too much time here because it's super simple and should make sense. Particle system is the meat of everything. So again, you can see it's very simple. We have an onUpdate function, we have a render function, and we have this emit function. So emit will actually emit a particle, just one particle. And the settings that it uses to actually emit this, or rather I should say the parameters that it uses, are these particle props, which stands for particle properties. So the reason that I've made this struct in the first place is because I don't want to have, 1, 2, 3, 4, 5, 6, 7, 8, 9 parameters all over here inside these function parameters. That's just way too much. It's going to be really hard to set. And also it means that by taking in a struct like this, I can not only have defaults, such as this like 1.0f, obviously you can do that with function arguments as well, but it's a little bit more complicated. Just because they have to be at the end of the function, whereas here I could, set a default position or whatever I want. But also it's really useful because I can reuse this same particle props to emit particles that should be pretty much the same. So when I'm emitting smoke, it's nice to have a little template and maybe only the position changes, but everything else stays the same. Maybe the velocity will change as well. That's what I did in that 1 hour game because obviously the ship's direction kind of controlled the velocity of the actual particles and which direction they would move in. But other than that, just by having this particle props here, it's really cool because I can just kind of create an instance of this struct somewhere inside my client code, and then I can just change only the parameter I'm interested in changing, and just keep passing that into this emit function to emit more and more particles, as you'll see in a minute. All right, so other than that, we have this struct called particle. This is what a particle currently is. This is what makes up a particle. So a particle at any given frame will have a position, a velocity, a begin and end color, a rotation, a begin and end size, lifetime, life remaining, and whether or not it's active, because this ties in, and this active boolean really ties in with this particle pool, because what we want to do is create a pool of particles. What you don't want to do is every time you need a new particle, create a new particle. Because by doing that, it's just going to dramatically slow down everything that's going on. What we want to do is basically pre-allocate this pool of particles and then continually reuse that array. That way there's no memory allocation, everything's kind of contiguous in memory, it's just going to perform a lot faster. We have this pool index, which is basically the index of the currently active particle. Now, or rather the next active particle. Or the next particle, I should say, that will be active once we actually emit it. So what we do, interestingly, here is we start at the maximum size. If I go over to the C++ code, you'll see here that the particle pool has a size of 1,000 particles. So obviously, because this is running it in an hour, it's hard-coded to be 909 here, because that's the last possible index. And the reason we start at index 909 and not 0 is just because when we render this, we should be rendering it in reverse order so that everything can blend together properly, especially when we start dropping those alpha values. If you don't do it that way, then you'll get artifacting, where basically it won't blend correctly with anything because it doesn't know how to. All right, anyway, and then we just have some basic stuff here to actually render the particles. So because I'm not using any kind of engine here, I'm just using this OpenGL library that I've made. We have to do all of the OpenGL rendering ourselves, which is fine. There's not that much to do, but we basically need to have these things here. Okay, cool. Let's dive into this. Obviously, onUpdate is a function that will be called every frame, as will onRender. So onRender just takes in a camera, whereas onUpdate is what does the actual, particle simulation, and that's why it takes in a time step. Okay, into the C++ code. So again, in the beginning, we just resize this particle pool to be 1000 particles. So this is not like reserve or anything, it's resize. It will actually instantiate 1000 particles, which is really nice because again, we already have done that. There's nothing that needs to be done when a particle gets emitted. It's all kind of pre-allocated, pre-instantiated. And then in the onUpdate particle, actually, let's look at emit first, probably, because I think that'll make more sense. And I've got some weird like errors here. I don't know if I accidentally pressed something. I don't think I did. I mean, I did that, but nah, I don't know. It's probably just nothing. Yeah, it is nothing. It's just Visual Studio. So what does emit do? Well, emit's job is to actually create a particle, but the particle already exists. It just needs to basically reuse or recycle an existing particle in memory. So what it does is it queries basically the active pool index, which is where are we up to in this particle pool? What is the next index we can use? And then inside that particle pool, using that particle pool index, it retrieves a reference to a particle. So this is now basically a blob of memory that represents this new particle we're emitting. Step one is to make it active so that it will get rendered and updated. And then we can basically fill out the rest based on the particle properties that get specified. So again, really simple stuff. Position obviously just sets to position. Rotation is kind of hard-coded here. You can't customize it through particle props. This was basically the same as that 1 hour game, as I mentioned, and I did not care about rotation. I just wanted it to rotate. I didn't care about the rate. I could just hard-code that. And you can see this is an example of using that random float function. Then we have the velocity, which again is just completely random here. The velocity variation controls how big we can vary our velocity. So you can see we kind of start with a base velocity and then we add on to that a number that kind of by default will be a number between negative 0.5 and positive 0.5. And then that will get multiplied with whatever the variation is. So in other words, if we say that the variation is 2, meaning we can kind of go within two units or 1 unit either side of 0, right? We can add that on here, then that's what it will do. So in other words, if I actually specify a horizontal velocity variation of 2 and then an initial velocity of 1, what that means is that since I'm going to add that on, I'm going to get a final velocity somewhere between 0 and 2 because it's going to add on 1 or subtract 1 or any number between that range from that kind of base velocity. And you can do that kind of separately on each axis, which is really nice because you can use it to simulate gravity. So in other words, if I have a velocity variation, I can make that velocity y be always negative because it has to be negative potentially because I always want the particles to go down, maybe just at different rates. Color begin, color end, super simple. This is just the color over life. This is the lifetime. We also have to keep track of life remaining because according to the life remaining, that's what we actually, lifetime is the total lifetime, but we also keep track of life remaining so that we can actually figure out the percentage of life that has passed. And we need that so that we can properly figure out, any kind of lerping, I guess, functionality. So anything that needs to linearly be interpolated over life, such as the color or like the alpha as well, or the size, anything that has a begin and end, we need this so that we can figure out at what kind of stage of its life that particle is at. Size begin, size end, again with the variation thing, super simple again. And then we have pool index. So we decrement this and then we mod it by the size so that it wraps around to 999 again if it needs to. And this will basically, the purpose of this, I guess, is just to set up the pool index for the next particle so that when we emit the next particle, we know the index in memory where we can actually write particle data to. Okay, cool. Super simple. On update. This goes through the entire particle pool. If it's not active, it continues. Now, it could potentially be safe to just break at a certain point. The reason being that we know that if a particle is not active, if it suddenly hits something that's not active, it's likely that all the further ones will also be inactive. However, this requires you to know the starting particle index, because if you picture the particle pool as like a little window in memory that keeps moving. And in fact, as I'm saying this, I'm realizing that there's so much to explain here and not much time. So maybe I'll make another video with like diagrams and stuff, but let me know if you want to see that in the comment section below. But basically, because of that, we need to know the starting index if we want to break. So this is just a lot easier, obviously, to do and a lot safer. So if the particle's life is gone, it's dead, then we can just set active to false and continue. to the next particle. Otherwise, very simple what we do in onUpdate. We just subtract the life remaining by the time step because the life remaining is in seconds. And the life that you specify for a particle is in seconds. So if I set the life to 1.0 as it is by default, that's 1 second. Position and rotation, obviously we increment the position by the velocity times the time step, and then the rotation as well by a hard-coded 0.01, which is in radians, multiplied by the time step. All right, rendering. Now this is a really simple hack here. I have a little if not mquad va, which basically means if the quad vertex array, which is this, is set to 0, means we haven't created the vertex array yet. So we'll go ahead and do all of our initialization code. I didn't want to do this here because the particle system is meant to be used as a stack-based variable, which means it can definitely be initialized before or instantiated before OpenGL has been instantiated, which means we can't do all of this stuff. OpenGL been initialized. Initialized, instantiated, you guys get the point. So I couldn't put this stuff in the constructor, and I really did not want to write an init function. So this is just a nice, easy way to be like, okay, well, before you render, let's just make sure that you can render. I'm not going to go through this stuff. It's really basic rendering code. This creates a quad. That's it. It creates a quad and it retrieves uniform locations. So uniforms like the view projection, the transform, and the color. That's it. It's super simple. Nothing to talk about at all. So use program, and this is, again, uploading the camera matrix to that particle shader, which we might look at in a second. And then the particle pool. So this goes through the particle pool. And again, what we've done is, and this is the cool thing here, when we emit a particle, we go through it backwards like this. So we can actually go through everything forwards, which is technically better because I don't think, we might not be, particles could get emitted quite often per frame, but we're definitely not going through the whole pool to emit particles. Whereas to update and to render, we definitely have to go through that entire particle pool, which means that I don't want to go backwards because that wouldn't be very good for memory access or anything like that. So we can still go through everything forwards, which is great. It's just that they get emitted from the end, which again, if you don't have a screen full of particles, might be a little bit not good because it has to continue past a whole bunch. And in fact, that's another reason why I said you have to know the starting particle if you want to break. Okay, fade away particles. So here, all we do is we lerp between the color end and the color begin, right? So that we figure out what, based on the remaining life, what the color should be. And then we also multiply the alpha by life. So life will be a value between 0 and 1 because we're dividing it by the total lifetime, the current lifetime by the total lifetime. And then this will basically make it so that it just fades out to 0 alpha by the end of its life, linearly. Okay, float size. Again, lerping between size end and size begin based on the life. Same with, no, that's it. That's all the lerping. And then rendering, obviously, all we do is just create a transformation matrix here with the position, the rotation, and the scale, because obviously size is also something we care about. Then we upload those uniform matrices, and this is, well, one uniform matrix, which is the transform, and then also the color, and the color is just a vec4. And then we render one single particle. Now, obviously this is not efficient because you would want to render all of the particles in one draw call, very likely. Like literally all of them, definitely, I think. And well, in this case, there's only 1,000 max, so definitely all of them in one draw call. Whereas we're not doing that. And again, that's just because the 1 hour kind of time constraint, and also because this is based on that 1 hour game and Hazel did not support batching at all. There is currently a batch rendering OpenGL series going on my channel. Definitely check that out. I'll have it linked in the top right corner. That's basically the technique I'm talking about, where we actually batch everything together into a single draw call instead of rendering all these particles separately, because that's a lot slower, and that will definitely limit just how many particles we can have on the screen at once. Because if we use up this entire particle pool, that's 1,000 particles, 1,000 draw calls, which is already kind of getting up there. Okay, that's it. I think that's it. Now the shader is not that interesting. It's just this is just a normal vertex shader, nothing special at all. And the color shader is also special. Surprise. I mean, not special. It's just literally setting the output color to be that uniform color that we specify. So super simple stuff. And then the really simple, I guess, sandbox layer that I wrote, which is again really simple, as you can see. All that does is enable blending, which is really important because we want to be able to fade the particles out and we need them to blend with each other properly and with the clear color as well. And This is what I was talking about and how good it is to initialize this kind of particle props, or rather to kind of have this particle prop system, because I can just set up all this stuff here. And again, you know, the color begin and end of each particle that I generate, it's going to be the same. So why would I keep setting that, you know, all the time? I can just kind of store it here. And then if I want to actually emit a particle, I can just do particle system emit. And then, yeah, just setting this stuff up. Again, you can tweak it however you want. You can expose it to IMGUI and play around with it if you like as well. This is just me making sure that we can resize. If we resize the window, our GL viewport will be resized as well. And then on update, clears the color. And then if the left mouse button is pressed, what we do is we basically, so most of this code is to figure out the particle position. The reason is we have a camera, we can move the camera around, we can zoom in and out, and we can resize the window. And so because of all these floating parameters, and because we can literally move the camera as well, we want to, well, the example I've gone with is when you click it, it emits particles at your mouse cursor. Because of that, I obviously need to have all this code to figure out where in world space I should be emitting the particles. And then that's it. And then what I do is I emit 5 of them at once, because why not? Just to make it a little bit more particles and more fun. And also because they obviously have velocity variations, size variations, all of that stuff. So if you emit 5 particles, they'll all be a little bit different, but they will originate at the same position with the same color and all of that stuff. Cool. Then I just update the particle system once per frame and render it once per frame. That's it. And I've added some IMGUI controls, because why not? So we can customize the birth color, death color, and the lifetime. And of course, feel free to play around with that however you like. Okay, and with all of that said, let's launch this and take a look at what I was able to do in under an hour. Okay, so here we have this kind of OpenGL Sandbox thing here. If I click and drag my mouse, it will emit particles, and I can zoom out. I can move the camera as well. So you can see I'm moving the camera here. Yeah, that's pretty much it. Pretty cool, right? So we have all of these particles being emitted from my mouse cursor. And then if I'll try and kind of full screen this. So I'll resize it to be the full screen. That obviously works, and we can kind of have all of that stuff here. So let's play with lifetime for fun. So you can turn this way up. So like this will be like, 13 seconds, which as you can see is quite a lot before it kind of fades out. And also I don't think IMGUI blocks the controls. But you can also make it really short. So like 0.3 seconds, which is kind of cool as well. So that's kind of customizing the lifetime. I'll just take it back to like 2 or something. And then we have birth color and death color. So I can set the birth color to like white, the death color to black or something like that. And now you can see they kind of fade out to black. Or I could make them fade out to like pink or something like that, whatever you're into. Or we could even do something more fun maybe by making it kind of go maybe red to blue. And that way it will kind of become purple before it goes blue. That's pretty cool. So there you go. That's the particle system, 1 hour, really simple stuff. And then you also have like all this size variation and stuff going on. And obviously you can add so much more to this, but this was just kind of a simple, I guess, example. And yeah, looks pretty cool. So that is the particle system in 1 hour. And of course, I'll have a download link for all of this code in the description below. Let me quickly see if I can just draw like a little Cherno logo. Hey, there it is. Pretty cool. Honestly, that was not all that difficult, and it took me 57 minutes. And I mean, I added a whole bunch of stuff in the end just because I had extra time. Now, obviously we are dealing with a rather simple particle system with plenty of limitations, but the point is, something like a particle system is super easy to just smash together like I just did, and it can just massively improve the visual quality, the visual fidelity of your games or any kind of graphics that you're working on. Not to mention they're extremely fun. Like I'm just gonna probably keep tinkering with this for a while just because it's fun. Now I mentioned several times that this is not like an optimal way to write a particle system, and that's due to a number of reasons. In fact, I might make a little bit of a particle kind of mini series. Let me know if you want to see that in the comment section below. Just explaining how this kind of all works and how to build it maybe step by step and how to improve it over time. But one of the reasons that it's not optimal is because everything is rendered as a separate draw call, which is terrible. I'm currently doing a series on batch rendering. Check that out if you haven't already. That's basically where we take all of these squares and we put them into one draw call. That massively improves the number of particles we can actually have on the screen at once, because if I push this too far, it's just gonna take too much time and we're gonna start losing frames. The other reason is just with how we process data and the kind of for loops and just the layout basically in memory. It's not optimal for CPU caching or anything like that. We might talk about that later as well. But the point is, it works. And I want that to be like a takeaway for a lot of people. People just tend to overcomplicate software engineering for no apparent reason. Maybe just to look cool or something like that. The simplest solution is like always the best. If you can write something and it works and it's really simple, the more simple it is, the better. Because apart from other people having to deal with it and also you being able to move on with your life instead of spending your whole life redesigning this particle system to make it the most complicated best thing ever, which probably won't be anyway. It'll be nice and simple and easy, everyone will understand it, you'll be able to move on and it will work. So in other words, what I'm saying is that yes, this is simple and it does a lot of naive kind of what other people would say are stupid things, but it works well, it looks great, and it performs adequately. So there's no reason to overcomplicate things for nothing. Anyway, let me know what you guys thought of this video. If you have any other kind of 1 hour challenges or maybe even 24-hour challenges, if there's something a little bit more complicated, let me know in the comment section below because I really love doing stuff like this. It's a ton of fun. Don't forget to check out Surfshark. There's a link in the description below that'll save you 83% and also give you 1 month for free. Make sure you use the code Cherno. Make sure you guys stay safe online and I will see you guys next time. Goodbye.